session. So there's a lot of crowd. Okay, so let's get started with the second tutorial. The second tutorial is about exploring the lost landscape of learned optimization. So this tutorial is given by James Harrison, who's a research scientist at Google DeepMind. So James got his PhD from Stanford, and he works in learned optimization, meta learning, Bayesian deep learning, learning control, etc. So I think this is a perfect example of how to use methods like meta learning, but in this case for optimization. So thank you, James.
Okay, great. Thank you very much for the introduction. So I was telling the organizers that I actually did my undergrad here, and I haven't been in this room since intro to calculus, chemistry, physics, etc. So I'm hoping that this is a little bit more interesting than Calculus 101. But if it's not, then just fall asleep in your chair and I'll get the message. So what I'm going to be talking about today, as was just mentioned, is learned optimization. And so what do I mean when I say learned optimization? And at its core, what this means is drawing a black box around the optimization part of neural network training. So where you would slot in Atom as some mapping between gradients and parameter updates, replacing that with some sort of learned function. And so a good question is, why would we want to do that? And the central idea is that there's a lot more interesting functions than we can learn than the simple heuristics that we can design. Okay. So before I get started, I just want to call out some contributors and state a few disclaimers. So the three people that you see here in particular, Luke, Daniel, and Joshua, were very core contributors to this work. Luke in particular worked on this for 5 years, so a lot of the work you're going to see is their work. And then there's a whole sort of small army of people that have also contributed to this project in various ways. So some quick disclaimers. First of all, this tutorial is heavily based on our work. So there's tons of great work that has worked on learned optimization that we're not going to focus on. We'll try to mention it in passing, but this is just going to be primarily based on our experience. We're primarily focused on optimizing neural networks. There's a lot of other optimization problems in the world, as I'm sure you're all aware. In particular, combinatorial optimization has been a big focus within learning optimization. And there's a whole great literature on that we're not going to touch at all, but I definitely encourage all of you to take a look at it. There's many important questions that are still unanswered. So for those of you that are PhD students, this should be exciting. I'll try to mention them wherever possible, but if there seems like there's sort of big gaping holes in what I'm talking about, that might be because there's no clear answers to them. And as I said, I'll mention them as much as possible, but I also encourage you to ask questions as much as possible during the tutorial. I know that the mic situation is a little bit challenging. Feel free to just raise your hand and I can repeat the question back into the mic and we can maybe have a bit of a back and forth. Okay, so what are we going to talk about today? So first, what is learned optimization? I already gave you a bit of a preview, but we'll dig into it a bit more. Why is it hard? How are we going to estimate gradients to train our learned optimizer function? How are we going to get data and how does that training actually progress? And what kind of architectures are we going to build to do optimization? Quick break. I'll take you through a very quick demo. I'll give you a view of the state of the art right now, and then we'll wrap up and talk about open questions. Any questions before I get started? Great. Okay, so this is maybe the last room in the world that I need to sort of sell on this point, but we're moving from a paradigm of hand-specified elements to learned elements or meta-learned elements. So as I'm sure most of you are aware, for a long time in the history of deep learning, a lot of people spent a lot of time engineering features. And that was gradually replaced with learning features. And despite all of the best ideas that went into the design of features, learned features simply are better given enough compute and data. However, within the neural network training pipeline, we're still hand designing optimizers, we're still hand choosing our loss functions, We're still hand specifying our architectures, and we're still hand specifying our regularizers. So the entire rest of the deep learning stack, other than feature learning, is still hand specified in a sort of dark art way. So I think what is possible is moving from an engineering to learn pipeline to a learning to learn pipeline. So this is meta learning in a sense that a lot of you are familiar with, but a bit distinct from meta learning in the sense of MAML. This is trying to learn the whole training pipeline. Okay, so when we're talking about learned optimization, let's consider starting with some weights of some neural network W. And how are we going to evolve those weights over time? We're going to take those weights, get some sort of loss, get the gradient of that loss, and then take a step with respect to the gradients with respect to the parameter. So W minus alpha grad L. This should be familiar. This is just SGD. And this is controlled by some parameter alpha. So what does our training pipeline look like? After applying SGD for one step, we have W1. We can apply this again and again and again until eventually we get some weights after training for an extended period of time, and we measure our performance, and we decide whether or not we like the network that we've trained, and we might update alpha accordingly. So this is sort of the most primitive neural network training pipeline you can think about, where you're just doing SGD, and then you're evaluating whether you've chosen good hyperparameters in your optimizer and whether you want to update them or not. So now let's look at learned optimization. We're replacing that optimization function that maps between subsequent weight values with some learned function that's taking as inputs gradients and outputting changes in parameters, or delta W. And so we have the same loop where we're going to unroll this optimizer for multiple steps and measure performance at the end. The actual structure of this function is going to be some gradient for each parameter or each weight in your network. You should think of the number of parameters as we're going to basically batch over that. That's going into some neural network, and the delta W is coming out. And that has parameters theta. So those are meta parameters. So as I said, we're going to take each target weight matrix. We're going to reshape our gradients. We're going to apply the same network in a batch form to those gradients, and then apply that weight update. And this is our learned optimization loop. Given the performance of at the end of training, we can now update our theta. So this is the meta parameters of our optimizer, and roll it again. And so we're going to loop that for multiple steps to learn the parameters of our optimizer. Are there any questions on this? This is an important part of this tutorial. Okay. So as a bit of an aside, this is taking a somewhat different view of optimization than may be familiar with you, and it's fundamentally optimization as a decision problem. So really at its core, optimization is a partially observed sequential decision-making problem, or a POMDP. And concretely, your observation is some sort of parameter value as well as associated gradients that's giving you local information about the function in question. Your action is some sort of update to your parameters, and then you have a cost function that is some view of your stage cost, or possibly your validation cost, or possibly some other metric. But it's some sort of cost function that is stage-wise. And really, your state of this is some more global information about your function that's not available to you. So in the same way that for control for a long time, a lot of control problems can be posed as POMDPs, for example. We use very simple heuristics. Pid works exceptionally well, but it turns out you can do substantially better by building sort of more mature control structures, or moving to something like reinforcement learning, where you learn a control policy via interaction with the system. And what I'm proposing is basically the exact same thing. We're moving from Atom to learning an optimization function. Okay, so to jump ahead for spoilers of where we are now, and you'll see this in the second half of the talk, our best learned optimizer right now, and this is a general purpose learned optimizer, is called Velo, and it's shown in the red line here. And this is evaluated on a set of 82 test tasks or neural networks. And what we're showing here is the speed up over a tuned Atom baseline. So this is, you choose a bunch of different hyperparameter values for your Atom, you choose the best one, and then you look at how much your learned optimization speeds you up in terms of getting to the same loss over that Atom baseline. And what we see is that for more than 50% of these tasks, we're at least 4 times faster, and we're pretty much uniformly better than Atom. So that's the state of where we are right now, and talk more about this later in the talk. Okay, so now that I've hopefully sold you on why this is exciting, why is it hard? What problems remain open? So the first is that unrolled computation graphs are extremely difficult to optimize. And this is also at the core of a lot of issues in recurrent neural networks and why they've sort of been replaced by transformers in part. And that's you evaluate the same function over and over. This often causes your loss landscape to get kind of crazy. So what we're visualizing on the right is we have some inner task. So this is the network that we're optimizing. And that's training a 2-layer MLP just on MNIST. Our optimizer architecture is just a very small, simple neural network. And the meta loss is just the final training loss. So we're optimizing with respect to the final training loss after application of our optimizer for n steps. So this is our meta loss landscape after 1 step, 2 steps, 3 steps, 5 steps. So far, so good. 7 steps, 10 steps, 13, 15, 18, 20, 25, 30, 40. And when we get to 50, so this is only 50 applications of our optimizer, we basically have so much fine-grained texture in our loss landscape that any notion of a local gradient has lost all meaning. So pure gradient descent, as you had probably experienced in or you use in standard training, is not really effective anymore. Another reason why it's hard is the training pipeline, as I've laid it out, it has basically quadratic complexity. So the way I pose to train these things is you roll out a full optimization problem. You compute the gradient with respect to that full optimization problem, maybe with respect to your final loss, for example. You update your parameters, and then you start all over again. So every single step of your outer training corresponds to a full training run of your inner problem. So if you want to train on relatively large networks, this is understandably super, super expensive. Meta generalization is something I'll talk about more later in the talk. But in the same way that you want to train some neural network that you train on ImageNet and want to generalize to some new classes or new instances of the same class, meta generalization across optimization problems is also an issue. Both different versions of the same optimization problem, so maybe keep an architecture fixed and change the data set, or substantially new optimization problems. So Atom works extremely reliably across all different kinds of neural network problems, and we would like our optimizers to do the same. Cool. So now that I've convinced you that gradient estimation is a hard problem, how do we actually do it? Okay, so idea 1, just use backward mode autodiff, so the same autodiff that you use for training a neural network as usual, which is doable because every single step of our optimization is differentiable, right? So we're taking a gradient, we're passing that into some neural network that's giving you a delta W to get your next set of weights, and you can backprop through that whole process. If your autodiff package is like reasonably mature, you can handle the Hessian vector products that occur, but it's not the end of the world. But a bunch of issues come up. So as I was saying earlier, it's highly sensitive to the chaotic loss landscape. So when you have this super fine-grained texture that is shown in this sort of simple sinusoid on top of a quadratic here, local gradients start to be basically nonsense. They go all over the place. As I said, you have quadratic complexity for training. And even worse, in autodiff, you have to store your activations in your forward pass. So you have to retain activations all the way forward through your long computational graph. And then to backprop, you have to use all those. And so when your activations correspond to things that have the size of all of your neural network weights, this becomes extremely expensive. Okay, so backward mode autodiff was looking a little bit sketchy. What if we use forward mode autodiff? So for those of you who maybe aren't familiar with forward mode autodiff, basically what you do is you only have to evaluate your neural network forward, and it gives you a directional derivative. So you specify a direction, you evaluate your network forward, you get the gradient, the directional derivative in that direction, and then you don't have to do the actual backprop. So we still have this sensitivity to chaotic loss landscapes. We still have quadratic complexity for training. We no longer have to store activations, so our memory expense is substantially lower. So that's a big improvement. But as I said, we can only compute directional gradients. So as you can imagine, when you move to high-dimensional weight spaces, high-dimensional meta parameter spaces, so large optimizers, your directional gradients start to be less and less informative. So if you have a billion-dimensional space and you're computing directional gradients, there's not a lot of information in there. So you might have to sample a large number of directions to get a good estimate of your gradient. Okay, idea 3, variational optimization. So what is variational optimization? The idea is that we're going to define a distribution over our parameters. So this is our meta parameters. We're going to convolve our outer loss surface with that distribution. It's going to suppress the high frequency structure and result in a modified outer loss. And so what do I mean by this? What you should be thinking when I say this is basically we're going to blur out this image on the right. So we're going to convolve that with a Gaussian, corresponds roughly to squinting at it, and get only the underlying low frequency structure and try to suppress the high frequency structure. And so concretely what this consists of is we have our loss function L. We're going to basically randomize the parameters theta. We're going to draw them from some distribution, and theta here again is our meta parameters. So this is the parameters of our optimizer. We're going to randomize those and compute the loss in expectation over that distribution of perturbed parameters. Okay? So as I said, we're going to sample some parameters from some distribution, having fixed a distribution over our parameters, and we're going to compute the loss of those perturbed parameters. So what does this actually correspond to? There's two ways to compute the gradient of this expectation that if you've taken maybe a class of reinforcement learning should be familiar to. One is reparameterization gradients. So you write theta tilde as a function of theta and some epsilon, and then you can backprop through the expectation. So this is great, but what you can also do is what lies at the core of evolution strategies, which is basically zeroth order gradient estimation, where you do the reinforced trick. So your expectation is now the grad of your log distribution times your loss of your perturbed parameters. So again, this is exactly the same as policy gradient in reinforcement learning, except instead of perturbing your outputs as you do in RL, you are perturbing basically the weights of your policy. So what this quantity here is in the bottom right is basically a bidirectional zeroth order gradient estimator. So your epsilon has basically magnitude sigma. So we're dividing through by 2 sigma because you're perturbing your loss bidirectionally. And this corresponds basically exactly to gradient estimation via finite differences. Does this make sense to everyone? Cool. So the reason we do bidirectional perturbations to our loss function is that this form of antithetic sampling reduces the variance of your estimation. So if you Taylor span these terms, you have some linear terms that follow. Okay, so let's dig a little more into evolution strategies as a method to train. What do they give us? Well, our sensitivity to these chaotic loss landscapes is substantially reduced because we're taking finite length steps and then actually evaluating the difference between them. So that has much lower sensitivity to the high frequency noise. And instead, we're going to better extract our low frequency loss surface. We still have quadratic complexity for training, so we haven't gotten around that. We don't have to store activations. This is forward mode only. All we have to do is compute losses with respect to perturbed parameters, right? So first we sample parameters, we compute our loss with respect to those parameters, and then we get the delta. But we still only are computing directional gradients. So we have to choose which way to perturb our parameters theta and get the gradients in that direction. So what we can see, if we're comparing evolutionary strategies and reparameterization-based gradients, both within the lens of variational optimization, so both of these have parameter randomization, is that the variance properties are substantially different. So often early in training, your reparameterization gradient is substantially lower variance. Whereas late in training, your ES gradient has substantially lower variance. And broadly, what we see is that if your loss surface is smooth, reparameterization gives you lower variance gradients because you don't have to compute directional gradients, whereas for high curvature, high local curvature in particular, ES is going to give you lower variance. Okay, so we've addressed a few problems, and the question is, how do we get around this quadratic complexity issue? Because as you can imagine, if you want to train networks of any size, you need to get around this issue as opposed to training a network on ImageNet like 100,000 times. So our strategy is to do partial unrolls. And so what this means is that instead of unrolling all the way to the end, you are partially unrolling to some intermediate weight value. From this, you're computing your meta loss, which might be your average weights, it might be your terminal weight at the point where you're computing this meta loss, any number of approaches. But basically what you're doing is you are rolling part way out, you are computing your metagradient, you're applying your metagradient, and then you're continuing training. Okay? So it's this interleaving of your inner training and your outer training. So the pros is that this gives you more outer gradients, so one per sort of truncation length, and this accelerates your training, your outer training. But we haven't gotten around the directional issue of your finite difference gradient estimate is still inefficient. So you still have to choose this direction that you're going to compute your directional gradient. Yeah. So once you roll out partway and you compute your loss, you can update your meta parameters and then continue optimizing within the same run. So your inner training problem might experience several different values of your optimizer meta parameters. Does that answer your question? Yeah. Okay. So it turns out that there's some clever things you can do to improve this a little bit further. So you can reduce the bias terms from this truncation by being a bit clever about how you're accumulating error terms. So there are versions of this for forward mode autodiff, like Dodge, for example. But then there are also versions that we've developed, PES, ES single, noise reuse ES, that reduce the bias a little bit. But still, this question of directional gradients is unsolved. So the question of how you reduce variance is still an open and important one. Okay, and so what you can see is that PES, which is a bias reduction method that sort of is designed to do this truncated gradients, outperforms ES at training learned optimizers for some specified meta loss. Okay, so some of you in the crowd probably thought when I said, oh, look, RL is a sequential decision-making problem. You were probably thinking, well, then you should use RL. Why aren't you using RL? This is clearly an RL problem, which is a good idea, but there are some important limitations of sort of off-the-shelf RL methods. So the idea for RL would be, instead of randomizing the parameters of your optimizer, you instead can randomize the actual updates you're making to your neural network. So the output of your policy here, where your policy is the optimizer, is your delta W's. You can have that be stochastic. And that allows you to use policy gradient to compute your meta gradient. So since your updates are randomized, this is implicitly smoothing the meta loss landscape. It's not going to smooth the meta loss landscape in the same way that the randomization we do for variational optimization is, but it is going to smooth that meta loss landscape. It enables partial backpropagation through your compute graph. And so what I mean by this is you are computing backprop gradients through your actual optimizer with respect to your policy grad gradients, but you aren't computing gradients all the way through your compute graph. And so this is going to be a relatively more tolerable expense in your training. The variance depends on the size of the action space as opposed to the number of policy parameters. And this starts to be a big difference. So what we are typically doing when we're designing learned optimizers is our learned optimizers are relatively small, and the action space or the parameter space of the networks we're optimizing are very large. So, ResNets maybe have, I don't know, like 5 to 10 million parameters. So that would be your action space size for thinking about this in an RL point of view, whereas your optimizer might only have a few thousand parameters. So all of a sudden, your variance is going to be determined by your inner problem parameters as opposed to your optimizer parameters, which means you are at risk of substantially higher variance because we have sort of flipped it to high dimensional action space, low dimensional parameter space, which is quite different, obviously, from RL. And we no longer get variance reduction by antithetic sampling. So typically in RL, you would use a critic, so a learned critic, to reduce the variance in your policy gradient. But what that actually corresponds to in this case would be learning a model to predict loss for a given optimizer for all sorts of different tasks that you want your optimizer to train on. So this becomes a very difficult multitask sort of loss prediction problem that we haven't had great luck getting to work that well, but other groups have taken this approach. So this is a thing that people are doing in the literature, but not one that we've pursued too aggressively. Okay, any questions on gradient estimation before we move on? Okay. So when we're training our learned optimizers, the data corresponds to training runs. This should hopefully be clear. But what this means is that it's extremely expensive and we have to be a bit thoughtful about our data generation. There's no ImageNet of optimization problems. We can't grab runs off the internet. And even if there were, they'd be super high dimensional. So we have two strategies that we can use, one that's more online and one that's more offline. And this roughly corresponds to online versus offline as you would see it in reinforcement learning. So in online training, you are going to train by actively rolling out your learned optimizer on some sort of tasks that you're interested in. So your data is going to be generated online, and this requires some fixed distribution over tasks that you are controlling. So you need to be able to procedurally generate a set of tasks that you feel will result in sufficient generalization of your optimizer. The risk of online training is the same of the risk of online RL, is that you both risk slow convergence and you risk instability. So a small step in sort of an incorrect direction can compound over many steps and destabilize your whole training. This is sort of at the root of why people, John Schulman, invented, TRPO, PPO, stuff like that. Stabilizing online training is non-trivial. So the risk of instability is something that we're going to sort of come back to at several points in this talk. Offline training, on the other hand, is training by imitating, in some sense, existing optimizers. So one thing that would make a lot of sense is all of you are probably training neural networks right now. What if you just save all your checkpoints and we can train a learned optimizer on those checkpoints? There's a few limitations. So first of all, those weights that you would be saving, we need a reasonably dense sort of tracking of how your weights evolve over time. And that would become extremely expensive if you want to save a large number of them. So if you're training on reasonably large networks for reasonably long run rates for a wide number of tasks, that becomes extremely expensive to store. There's problems with instability due to distribution shift, the same as sort of standard offline RL. And it's not clear how much we can improve beyond the data generating optimizers. So a common strategy that we've used and others have used is the idea that, okay, we want to accelerate Atom, so we're going to try to get our optimizer to imitate 5 steps of Atom, which typically generates optimizers that are somewhat worse than a 5-step Atom, but better than a 1-step Atom. So this is great, but maybe not necessarily worth going to all this effort for when we think that there's much better optimizers that could be learned using other training strategies. So as I mentioned, for the rest of this talk, are going to talk primarily about the online training paradigm, but offline is still, I think, interesting. How you can best build on offline data, I think, remains a pretty open question. Okay, so in terms of building a training data set, what we're going to do is procedural task generation. So there's no real way around it. We're going to have to basically specify a generative process for all the tasks that we care about, and then hope that we get good enough generalization that we can work on your task of interest. So this is from a paper from 2020. There's a bunch of different families that you can see here. So MLPs, VAEs, convnets, simple quadratics, other autoencoders like denoising autoencoders, RNNs. We've certainly expanded this family to other things, like obviously transformers is a thing that people are interested in, other unsupervised learning methods, things like that. And then as you can imagine, building a larger distribution of tasks enables better generalization to new tasks. So this is the same as maybe training an adaptive policy on a bunch of different environments and then deploying that to some environment in RL. A wider distribution of environments enables better operation on some new environment. However, generalizing across scale is still quite an open problem. So all of the limitations that we've discussed in terms of gradient estimation are really amplified by large-scale models, right? So doing large-scale training runs is expensive. And so by and large, we don't include any very large models in our training set. And so we need to basically be able to purely generalize from smaller scale problems to larger scale problems, which is, I think, still a fairly open problem. Okay. And one additional element of the training pipeline is that our training is fundamentally multitask. And so what I mean by that is that your different tasks that you might sample are going to have fairly radically different gradient magnitudes. So this is just two random training curves that I grabbed from the Atom paper. And what you can see is that the sort of late training loss scales are dramatically different. The gradients will be super different. And for any different data set, architecture, anything, your gradients are going to be very different magnitude. And so what that means is that we need a way to be able to work over all of those differently scaled gradients. In addition to that, different tasks have different wall clock times for computing gradients. So if you think about wanting to scale up your training of your learned optimizer, you might have several different machines all running training runs and giving you gradients with respect to your optimizer parameters. Those might have different scales. They're going to be yielding meta gradients at different rates, which is sort of a practical element that becomes quite important in how you're balancing different tasks in multitask training. And what we're really doing here, like the core of what makes it hard is we're wrapping a dynamical system in another dependent dynamical system, and any instability in the inner dynamical system will often destabilize the outer dynamical system. So when you think of it from this point of view, part of what the takeaway should be is that, oh, we need to sort of balance that coupling between these dynamical systems, but also is we need to stabilize our inner problems and stabilize the bridge between the inner and outer problem as much as possible so that any instability in inner training doesn't, destroy your whole meta training run. So our solution so far is a lot of very simple ideas. So we often combine our gradients by normalizing magnitudes, so we're getting just directions. We have a predictive model for rejecting tasks that will take too long to train. So when we're procedurally generating tasks, we actually train a neural network that maps from a configuration for that task to an estimated runtime. And if that runtime is too long, we're just not going to train on that task because you might sample, a very deep network that's very wide, et cetera, maybe high dimensional data that would just take too long to run. It will sort of live on a machine giving really infrequent meta gradients and just not be useful and just overall slow down meta training. And we use a curriculum to control the impact of divergence. What I mean by that is that the most important element for us in the curriculum is gradually growing the inner problem horizon. So we start training only for a small number of steps, and then we gradually lengthen that. And that means if your optimization is unstable early on, there's only so far that you can diverge. So you're not going to get basically completely random gradients or risk, nanning out your machine, for example. But there's tons of room for improvement here. So this is like a set of hacks that we mostly developed to make things work. But there's a lot better ideas that could be done here, especially building on the literature for multitask learning. Any questions on this? So in addition to procedurally generating tasks, there's a question of can we augment our data or our inner problems to get better generalization? And if you've sort of tried to work in computer vision, this is something you're probably familiar with. There's a lot of sort of random crops and shifts and things like that lead to better generalization, and we're going to try to do roughly the same thing within optimization problems. And so what do we want to randomize in our task distribution? Well, we want to randomize our data set. We don't want to build the best optimizer for MNIST alone. We want to have optimizers that work over any data set you throw at it. We're going to randomize the neural network architecture, number of layers, nonlinearities, layer types, con versus densely connected versus self-attention, things like that. And we're going to randomize the loss function. So those are sort of the obvious parts that we're going to randomize in batch size. And then there's a whole bunch of other stuff that we can induce that's not maybe the normal things you would think about in terms of specifying a training run that can improve generalization. So we can randomize our tensor initialization. So as opposed to always doing the Keiming initialization or whatever, we can randomize it however we want. We can reparameterize weights, so we can sort of rescale the activations coming into a weight matrix and rescale the output to change the sensitivities of our loss with respect to certain parameters. We can lower the precision of certain weights, which sort of behaves in somewhat unusual ways. We can rescale or add noise to our gradients. We can compute gradients via ES or forward mode autodiff to give directional gradients as opposed to standard backprop gradients. And we can vary our problem run length. So there's a whole bunch of things we can do that roughly correspond to augmentations that you would see in computer vision, but are augmentations to the optimization problem. Yeah. Yeah, so the question is, does this do these augmentations make the meta learning task more difficult? The answer is definitely yes, in the same way that adding in a bunch of sort of random crops and rotations and stuff makes your training loss decrease slower in training a ResNet, for example. So it does slow down training, but it substantially improves generalization. Okay. So we've so far thought of a learned optimizer as kind of a black box that takes in gradients, outputs, changes in parameters. And we haven't thought much about how we actually structure that. So we know that maybe we want to batch apply it over all elements in our neural network or all weights in our neural network, but that's about as much as we've thought about it. So let's dig a little bit into how we should actually structure our optimizers. So what matters in choosing an architecture for an optimizer? And this is a sort of unusual question that isn't taught in Intro to ML. Oh, sorry. So what do we care about? We want a network that's inexpensive to evaluate. Because we have to, for a training run, evaluate this multiple times, the metric that we really care about is wall clock time, some trade-off of wall clock to performance. So we want something that's relatively inexpensive relative to its performance. We ideally want high capacity or an expressive network. This is obviously in tension with one that's inexpensive to evaluate. We want good generalization if possible, or at least the ability to achieve good generalization, so to not be bottlenecked in generalization ability by our architecture. And we'd ideally want stable training. So these are roughly what we care about when we're specifying our optimizer. These are mostly going to be the same as for a normal neural network, but there's a much greater tension between the cost of evaluation and the performance that you get for an optimizer because there's so many sequential evaluations of this network. So we have some work on this that was actually published at Cola's last year that basically exactly explores the trade-off between the achievable meta loss and the time per step, or the memory required for an optimization step. So what you can see is in the top left of most of these curves is SGD, so that's the sort of upward facing triangle, super low time per step, super low memory cost. Makes sense. SGD with momentum, a little bit better meta loss, a little bit more time per step, a little bit higher memory, et cetera, et cetera. But what we can see is there's a clear Pareto frontier that defines the trade-off between these quantities, and that trade-off is going to be basically unavoidable. We don't know where the Pareto frontier is. So part of designing an architecture that we care about is moving that Pareto frontier. But we know that there is some best achievable optimizers that live on the sort of true Pareto frontier. So we want to do as well as possible trading off these things, and we want to be conscious of the trade-offs between performance, time per step, memory. So as you can sort of intuit, a good but expensive optimizer is often going to underperform even a relatively simple optimizer when you get down to wall clock time. And wall clock time is really what we care about. You want your problem to train fast. So our strategy in practice is a few tricks. We're often going to use very small neural networks to process some sort of input features, and I'll get to those features in a second. So often what we're using is just something really simple, like a small two-layer MLP, and this is acting batch-wise, as I said, on all of your gradients coming in. And often these are going to be so small that they have a single-digit number of hidden units. So extremely small MLPs processing things. We're often going to exploit hierarchy. So in addition to a super small per weight MLP, we're often going to also have a per tensor neural network that might be recurrent. So this is maybe aggregating features of your gradients and then using that to control your lower level things. So you're going to amortize computation over different sort of levels of your tensor. And then feature design matters a lot. So as you can imagine, if you have just a super small MLP, you can't throw in raw features and expect it to be able to learn to process all of these features. You often want to give it as much of a head start as possible. So you do need to think a little bit about what quantities would be relevant to an optimizer. And what this often means is things like exponentially weighted averages of gradients, possibly at multiple timescales. So this is sort of like the momentum terms that you would see. What the shape of a particular tensor is, how far you are in training, normalized gradients, things like that. So there's tons of quantities that you can design to feed into your network. And then just one sort of takeaway is that the trade-offs between these quantities, between performance and time per step or memory usage and things like that, are in fact task dependent as well. So this is something that you want to think about across a distribution of tasks. So we can make that a bit more concrete here, where we're comparing meta-training on MLPs to meta-training on convnets. So in the top two left figures are MLPs, and the top two right figures are convnets. And we're plotting basically speed up over SGD. And what you can see is that for different optimizers, the dependence on batch size and hidden size of the optimizer are quite different. And so implementation matters, the underlying tasks matter. There's a lot of different considerations that go into the trade-offs between these elements, and it's really important to think carefully about. Do you have a question? Oh, okay. So similarly, in the bottom figure is just a simple visualization that plotting a learner optimizer versus number of steps. So the bottom right two figures, plotting versus number of steps might give some perceived performance, but plotting versus wall clock time might be substantially different. Luckily, what we typically see is that as you get to larger and larger neural networks, the cost of these learned optimizers is smaller and smaller. It's dominated by the cost of computing gradients of your network. And so what we see is that the thinking of performance via inner training step as a sort of base to evaluate them becomes more meaningful as you get to larger inner neural networks. But thinking concretely about the cost of evaluating your network remains important. And then there's this question of generalization. So generalization in supervised deep learning, there's a few sort of standard ingredients that go into the recipe, right? So we're going to take a broad data distribution, and again, this is supervised learning. So training a good ResNet, for example, you're going to take as broad a distribution as possible. You're going to add some regularization to prevent overfitting. You're going to choose an architecture with appropriate inductive biases. So convnets are very well structured to image tasks or vision tasks. And then you're going to add in some element of gradient control. And I sort of separate this from inductive biases and regularization because I think it's doing something different. So what I mean by gradient control is adding in things like residual connections, adding in normalization like layer norm, batch norm, things like that. And what this is going to give you is gradients that have sort of appropriate magnitudes. Generalization and learned optimization, on the other hand, we still want a broad data distribution where this is, again, a distribution over tasks, as we discussed earlier in the talk. We still want regularization, and we still want to be careful in our architecture and the inductive biases it induces. And we still want to control our metagradients, but these are all somewhat open questions now. So the question of how we best do these is largely not settled. And I'll talk a little bit about how we do it, but I think the question of achieving these is still quite open. And so the sort of one-line way I've been saying that is that we really don't have the convnet of learned optimizers yet. We don't have this sort of sledgehammer architecture that works across a broad range of scales and that really reliably is giving us the biases that we care about. Okay, so one inductive bias that we might care about is stability. As I said, what we're doing in learned optimization is we're wrapping a dynamical system in another dynamical system, and any instability in either parts of these can blow up the whole thing. So resonance and transformers work in part because they control gradient magnitudes, and we want to achieve the same thing in learned optimization. However, residual connections, layer norm, things like that are not sufficient to achieve sort of magnitude controlled gradients. We need to actually think about the dynamics of the coupled optimizer-optimizee. So just as an illustration, most of you have probably seen this, but visualizing the landscapes associated with different neural networks, adding in skip connections dramatically improves the quality of the gradients you're going to get out compared to without skip connections. So one approach is drawing insights from the noisy quadratic setting. And what the noisy quadratic setting is a standard quadratic optimization problem where you are sampling basically the mean of that problem IID for every step in your inner optimization problem. And what this corresponds to is roughly mini batch optimization on a quadratic problem. And this is a relatively standard setting in which one can do some optimization theory, and it seems to transfer relatively well to neural networks. And so what we find is that biasing optimizers towards stability has several benefits. So it reduces gradient variance, it accelerates training, and it improves generalization. And so we can show this in a few different ways. So on the bottom left, we're plotting the variance of the metagradients as a function of basically step size, where step size is being swept from very small to the limit of stability. So once your step size is above 2 over the max eigenvalue of the Hessian, your optimization is unstable. So what you can see is that when you are taking steps that are relatively within the stable zone of your inner problem, your metagradients become much better conditioned, and the variance of those metagradients is substantially lower. So really what this is telling us is that when we stabilize our inner problem, it substantially stabilizes our outer problem. And the variances of these two dynamical systems are extremely tightly interlinked. What we see in the middle plot is basically as you bias a learned optimizer towards something that looks like Atom, which is an extremely robust optimizer, it substantially accelerates training. So what this roughly means is that, especially early in training, if you make your learned optimizer look more like a standard optimizer, especially those that have been found to be extremely robust, this accelerates training and reduces meta gradient variance. And the meta losses are shown in the right plot. So the root of this paper, which I'm sort of skirting around and not getting into the details on, is that we want to consider stability. What the actual paper consists of is a lot of stability on this quadratic problem. So relatively standard optimization theory, or it looks a lot like control theory for those from control backgrounds. And we take away a few insights. So biasing optimizers toward descent at initialization accelerates training. This is something that sounds like super obvious once I say it. And what I mean by this is when you are randomly initializing a neural network and taking gradients as an input, your neural network might go uphill on those gradients with equal probability as going downhill on those gradients. So this is not a good way to initialize your optimizer. So what you want to do is optimize or regularize your optimizer in a way that it is going to be biased towards descending your loss landscape. You can regularize your optimizer weights, which can control amplification. So this is something that looks more like layer norm, for example, or batch norm, or normalization of magnitudes in atom. So these are kind of the same idea, but really what you're doing is you are trying to achieve unit norm to prevent your long computation graph from massively amplifying your inputs. And it turns out that magnitude normalization of learned optimizer outputs can also improve stability. So a lot of the insights are things like batch norm, layer norm, things like that are also extremely useful for optimizers. And so concretely, what this corresponds to is for all of these plots, we trained a very simple learned optimizer on just one small MLP. So we only trained it on one task that's just an MLP. And then we evaluated it on several different tasks all the way up to ResNets. And so the orange curve that you see here is the black box learned optimizer. So this is sort of the off-the-shelf learned optimizer without any additional tricks. And the inner problem was trained to 2,000 steps, which is that black bar. And our optimizer, which is called star here, so that's green and red for different amounts of regularization, incorporate some stability-inducing structures and regularizations and things like that. And so what we see is we achieve substantially better generalization to novel tasks induced by this sort of stability-centric mindset. So this very dynamical systems view is really important for achieving good generalization with these optimizers, while still, I guess, not harming the capacity associated with them or the expressivity. Any questions on this? Okay, so I think I'm 3 minutes early to the break. Are there any questions before going to the break? In the sense that, so the question is, do we introduce new hyperparameters into the outer training loop? The learned optimizer has weights, right? So those weights are hyperparameters in some sense, but other than that, we aren't adding in other hyperparameters. So we ideally want the learned optimizers that we learn to be hyperparameter free. And so part of, this is sort of a philosophical point, is I think what a lot of us feel is that the training procedure for standard neural network training isn't just an optimizer running with a fixed set of hyperparameters. It's an optimizer running with either a human or like some sort of hyperparameter tuning system operating in addition to it. And that coupled is like your full optimizer. And so we're trying to actually put both of those in a learned structure as opposed to just the inner optimizer. So human beings are often part of the optimization process. You could also do like a grid search over your hyperparameters, and we're also trying to avoid doing that. But fundamentally, this interaction between the hyperparameter tuner and the optimizer is a really important part of modern machine learning, and we're trying to learn that as well. Yeah, so your question is, what is the value of this if something like Atom plus Bayes-opt is already an effective way to train things? So this is a totally fair question. I think that we have already started seeing speedups that are so large that they enable training totally new neural networks at perhaps scales that aren't imaginable, or iterating much faster on architectures or things like that. So I think if you accelerate neural network training, there's a substantial compute reduce, but there's also an improvement in sort of your time efficiency. So I think there's a lot of benefits to that acceleration. Yeah, so the question is, have we only tried small networks? We have tried larger networks, so more like medium scale. Something like a transformer is a somewhat challenging choice, just because you have to you'd have to look at every gradient across time, and that would be super expensive. So our work has focused on sort of small scale and medium scale architectures. We haven't gone super large. Other people that have worked on learned optimization have gone larger and have used transformers. And there's a wider array of architectures than the ones that I've focused on. Yeah, great question. So what you'll see in the second half is that our best learned optimizer right now is terrible at reinforcement learning, but like pretty good at everything else. There is at least one paper I'm aware of that focuses on learned optimization for reinforcement learning, and I think there's probably a couple more. So I guess one thing that I didn't really address here is that you can also, we have focused on training a very general purpose learned optimizer. You can also specialize a learned optimizer for a class of problems. So if you maybe have some system that you're deploying, like an RL system where you have new data coming in, maybe you're doing something that looks like continual learning, you might want to specialize an optimizer to that. And something you could do is specialize to reinforcement learning problems generally. Yeah, so your question is, have we considered restricting our architectures to something that looks more like, for example, natural gradient, K-fax, something like that? This is a great question. The restricting your optimizer from something that looks like a neural network to something that looks more like an optimizer, maybe with neural network components, I think is an extremely promising research direction. And there have been some works that have done this. So I have one project ongoing that looks a little bit more like KFAC, but has learned components in it. So that's sort of a more hybrid learned optimization method. And then there's other works in the literature that have also done this. So I think it makes a lot of sense. But really, and this is something I'll sort of mention in the open questions part of the talk, really what we're thinking about is these architectures for optimizers that might include learned components is a whole new class of architectures that we should be thinking about as a class of architectures, as opposed to this optimizer plus, controlling this hyperparameter, for example.
because I think I did the wrong way. I was actually asking about the class of the non-optimizers because you talked about that
questions.
Can I ask you a question based on the chat?
Yeah.
So the question in the chat is, are there any frameworks that you're aware of that actually mathematically, at least for statistics, the meta-learning optimizers will outperform non-convex? More generally, are there any frameworks?
I only caught the second half of that. It was the question, are there theory papers on meta learning optimizers?
Are there any theory that says that some classes of problems meta-learning optimizers will be better than?
Yeah, the sort of theoretical basis for our argument, I think, is that optimization is well specified as a partially observed MDP. And we know that some element of active exploration, or like trading off exploration and exploitation, is going to be necessary to, or like your optimal policy will actively trade off exploration and exploitation within POMDPs. So that's, you know, a statement from like Bayes adaptive RL, for example. So that's like the theoretical basis that I stick with. And then even for relatively simple like SGD learning rate problems, there's some theoretical work saying that like extracting optimal learning rates still needs forms of exploration. So even for very simple problems, actively trading off exploration, exploitation, actively sort of decaying learning rate or increasing learning rate as a function of what you're observing is necessary for optimality. And that's work by like Jeffrey Pennington and some other people at Google. So we know that even for like simple SGD on quadratics, there's like active trade-offs that you need, and then for much more complicated questions, I think there's like a reasonable amount of evidence. Is your question like directly related, or? Yeah, good question. So there's the practical elements and then the intellectual elements for me personally. As I was telling some people at the break, my background was like some meta learning, so you know, this community, and then some RL, some dynamical systems and control, things like that. And this problem is a very interesting combination of all of those that is very new. And I think there's a lot of sort of blue sky research that can be done here that's really exciting, especially if you find all those topics interesting. So that's the intellectual reason that I've pursued it. Practically, neural network optimization is extremely expensive in terms of the actual compute requirements and in terms of the human time associated with babysitting them and tuning them. And if we can automate those processes, it's basically a huge financial savings and a huge time savings, and will ideally accelerate, you know, development of AI systems generally and enable new neural networks that so far we haven't been able to develop. Okay, so after the break, I figured we could get, you know, into the weeds a little bit. And so I have a really simple notebook that I didn't have the confidence to actually live code it in front of you all. So you'll have to settle for stepping through this notebook that I made sure ran. But basically what this notebook does is a really, really simple learned optimizer implemented totally from scratch in JAX. So I'm not using any like neural network frameworks. I'm not using our own toolkit for learned optimization. It's like, even if you don't know JAX, basically this is just NumPy, and then occasionally I'll compute some gradients, which is basically all JAX is NumPy plus grad plus autodiff. So, or plus compilation. Cool. Oh, thanks so much. Okay, so let's import some stuff. Generally speaking, in this code, when you see JNP, that's JAX NumPy. So this is basically NumPy, but differentiable, and then ONP is just normal NumPy. But generally speaking, JNP just means Jack's NumPy. Okay, and the data we're going to work on is going to be MNIST, but resized to 8 by 8. So I need this to be cheap because it needs to run in a notebook in front of you all, so we can't do like a big distribution of hard tasks. But this is roughly what our data looks like. You know, as you can tell, this is a 4 probably, and this is maybe a 3, and I don't know what this one is. Well, we're not going to get to zero loss on this problem, but data is data. Okay, so we're going to put together a task, and we're only going to train on one task here. We're going to see different mini batches over the course of training, but we're only going to specify one small MLP. So as opposed, or in contrast to the, specifying a wide distribution of tasks that we talked about in the first half, for the purposes of this notebook, we're just going to specify one task. And that's just going to be a really small MLP. So to init this, we're going to specify 2 layers, weights and biases, and this init function just returns those weights all stacked up. So you have your 8 by 8 input, which is going to be flattened. That's going into a hidden layer of 128. That's going to be passed through some ReLUs, and then another hidden layer that maps to 10 dimensions. And then our loss function. So we're going to take our data in. As I said, we're going to flatten. We're going to grab our parameters, which are an input to our loss function here, and I'll talk about why that is in a second. We're going to compute our logits by just evaluating, weight matrix, bias, ReLU, weight matrix, bias. So this is just standard 2-layer MLP. Grab our labels and compute our cross entropy loss. So is this clear to everybody? It's like no surprises here yet. And then we're going to return the mean of our loss over some mini batch. Okay, so task throughout the rest of this notebook is going to refer to this MLP task, and we're going to grab our parameters, where params here is the weights of the neural network from the initialization. So for those of you who aren't familiar with JAX, when you call grad in JAX, you'll typically differentiate with respect to the first argument to some function. So params is passed in as the first argument to this function, and then we'll compute gradients with respect to that input. So gradients of loss with respect to parameters. Cool. So we can run this cell, and it should give us some warnings and our task loss. So we can see that our freshly initialized MLP has an average loss for some batch of 2.3. And if you are familiar with 10-way classification from MNIST, you'll know that that's like random prediction. Okay, so now let's define an optimizer. So what we're going to be working with in this notebook is really, really simple. And it's SGD with momentum. And the parameters that we're going to learn are the learning rate and the decay rate. So concretely, what the update looks like is your momentum is your previous time steps momentum, M, times your decay rate, plus 1 minus your decay rate times G. So this is sort of the classic SGD with momentum, beta M plus 1 minus beta G. Okay? And then, again, nothing too surprising here. Your parameters are being updated by your learning rate times your momentum. Okay, so LR is your learning rate, and decay here is your decay parameter. And what we're going to do in this notebook is meta learn those 2 quantities via local optimization. Other stuff to note in this optimizer. We are initializing our inner optimizer state. So our optimizer has the state, which is the parameters of the network, and then also the momentum values. And then we're initializing our meta parameters, which is just giving us our learning rate and decay back, and these are going to be updated. We are going to JIT compile our inner update. So if you're not familiar with JAX, that's, you can ignore. This is just going to accelerate our computation. Cool. So we can run that. Okay, we define an optimizer. And so now, as a bit of an exercise, let's try running this optimizer for a few different learning rates and seeing what our training curves look like. So we're going to specify a number of steps. So we're going to train for 1,000 steps. We're going to loop over learning rates in 1e minus 2, 1e minus 1, and 1. We are going to specify our optimizer as this SGD with momentum. We are going to grab our initial optimizer state. So again, that's your parameters and your momentum. And then we're going to grab our meta level parameters. So that's going to be just the learning rate and the decay. And then we are going to specify this function, value grad function, which is a compiled version of the JAX value and grad operation applied to the task loss. And what value and grad is in JAX is it takes as input a function and gives you a different function where when you pass in some argument, it gives you the function evaluated for that argument and the gradient at that argument. So does this make sense? This is basically getting your function value and your function gradient for some batch, for example. Okay, so then we're going to loop over some number of steps. We're going to grab our batch. We're going to compute our loss and our gradients. We are going to update our opt state with this update inner opt state function. So this is basically applying our optimizer. And so what this is taking in is our opt state for 1. So it's taking in the parameters and the momentum, and then it's outputting the updated parameters and the momentum. So this is sort of the state evolution box you can draw around an optimizer. It's taking gradients as inputs, and it's taking these meta parameters. So these meta parameters, again, are the learning rate and the decay. Okay, so does this make sense, everybody? That this optimizer function, applying this optimizer, is taking in the hyperparameters of the optimizer, the state of the optimizer, including the parameters of the MLP, and the gradients. Any questions on that? Okay. So from that, we're going to grab our losses and append them to some list, and then we'll just plot the losses. So let's see how this goes. Fingers crossed. Okay, cool. So training curves. This should hopefully be pretty unsurprising. This is just like a hyperparameter sweep over like a very off-the-shelf optimizer, so nothing here should be all that surprising. So what do we see? A learning rate of 0.01 is like clearly way too slow. A learning rate of 0.1 is pretty good, and a learning rate of 1.0 for this like super simple task seems to work pretty well. So if I asked you to hyperparameter tune this network, you would probably do a procedure like this of sweep over your parameters and choose one that looks pretty good via like a metric that kind of lives in your brain. And in this case, you would probably choose learning rate of 1. Okay, so now we're going to get a little crazy. We're going to try to train our meta parameters using our average loss over the course of a training run as our meta loss. Okay, so the way we're going to do this, despite me talking all about how you should use ES, variational optimization, PES, et cetera, we're going to use reparameterization gradients or like standard backprop through the full rollout, which works in this problem, but as you scale up, generally won't work all that well. So this is just basically a helper function that specifies a batch of or a sequence of input batches, so that this enables us to basically like scan over it later, which is kind of just like a fancy loop. It enables us to like compile our training run. And we're going to specify our meta loss. And so what our meta loss is, as I said, is going to be our average training loss over some horizon. Okay. So what this consists of, so this meta loss function is taking in the meta parameters, right? So this is taking in those meta parameters, which are the learning rate and the decay. And it's taking in some sequence of batches. And then this is doing a full training run in this meta loss computation and outputting those average gradients. So what step here corresponds to is some function that takes in some optimization state. It's getting your parameters. It's computing this value and grad function with respect to those parameters and giving you a loss and a gradient. it's applying your optimizer as a function of your metaparameters, your op state, and your grads. So again, this step function is basically one training step of the same form of training steps that we saw previously. So we've defined the step function, and so like a training run would be n of these step functions, all applied for some fixed number of metaparameters. So we'll then initialize our parameters. So this is our initial neural network weights. We'll initialize our opt state. So this is basically setting up our optimizer to have an opt state which consists of parameters and momentum values, where the momentum values are going to be just initialized at 0. And then we're going to do a scan over this step function, this opt state, and the sequence of batches. And if you're not familiar with scans, it's basically just a fancy way to do a loop where you iteratively evaluate the function that you pass as input with a state that's passed forward through that. It just is more efficient and is easier to compile, basically. Okay, so does this make sense to everybody? What the scan is doing is looping over time. So this is basically doing n training steps. And then what we're scanning over is this step function. So the step function is a step of training, scan over it, do n steps training. The output of it is all of our losses for every point in training, or like every single iteration of training. And then what this meta loss function is going to output is the mean of these losses. So as I said, our meta loss is our average loss over a training run. So just one more time, because this is like the most confusing part. The step function is one step of training. The scan is looping that for n steps. We're getting the loss function for every point in training, and then we're taking the mean of that, and that's our meta loss. And so we're going to use this downstream to compute meta gradients and do our meta training. Okay? Cool. So we can run this cell and get our meta loss. And we see that our meta loss here, which is our average over our losses, given a run length of 10, and these initialized metaparameters is 2.3. So over 10 steps, it doesn't train all that long. If we make this like 100 steps, and we maybe go to like a learning rate that we know works a little better, we can run this again, and our meta loss will be 1.4. So that's like, if we go back up here, and we look at this green curve, which is basically the hyperparameters that we just ran, that's like roughly the average loss for a run length of 100. So we're basically stopping our run there, and then we're averaging all of those losses. So 1.4 looks about right. Any questions on this so far? Yeah. Yeah, we totally could take the final loss. Using the gradient estimation strategy we use, it'll be less stable. So it's easier for me to do like a simple demo if it's just average loss. But you could totally replace that with final loss. Cool. Any other questions? Yeah. Yeah, exactly. So the final loss, when you think of like the sort of texture that I showed you in those meta loss landscapes, you get much more of this high frequency texture for final loss as opposed to average loss. Average loss is averaging across batches, but it's also averaging across like the dynamics of the system. And so basically you get a lower variance loss term for like those few reasons when you do the average loss. It just, like average loss is a meta loss that you can choose that often doesn't correspond all that well with what people really care about. What they really care about is some discounted notion. Okay, what they really care about is like, given some distribution over run length of like, I'm going to specify how long I think it might run for, what is my final loss? Something like that, right? So it's like a more complex object than something simple like this. But what we find is that average loss as a meta loss is like pretty effective at giving us optimizers that optimize pretty well. Often they can be a little greedy early in training, as you would maybe expect, because early in training they have the loss is relatively high, so it wants to push that down as fast as possible, and it maybe doesn't incorporate or like doesn't appropriately value small improvements later in training that you still would care about. So that's kind of the trade-off. Are there any other questions? Oh, yeah. Mm-hmm.
Do you think about macro? Shouldn't it be like the last step of your principle, or like last few steps of principle? Because if you initialize a parameter of a model, I don't think it's the first step of any like.
Yeah. Yeah. I think that's totally valid, sort of in line with what I was saying to these questions. Your meta loss can be kind of whatever you want. It's some view of a training run, right? And so the question is, okay, what do you care about in a training run? And the answer might be final loss, but it might be final validation loss. It might be some other metric. It might be some sort of like discounted notion of final loss. So there's tons of things you can care about. I agree with you that average loss over some horizon is going to often be like a little greedy early in training. And I think we'll totally see that later in this notebook. But here it's just like an easier thing to demo quickly. But the question of what like your best choice of meta loss is like a totally open and valid question. Any other questions? Yes. The reason that it's more stable, that average loss is more stable than, so there's two features. One is mini batch variance. So if you want to get a lower variance estimate of a meta loss that is your final loss, you could evaluate it on a whole bunch of batches or like your full validation set or something like that. And that would definitely help reduce variance. But another factor is you can imagine your optimizer is taking a sequence of steps. And if you change your learning rate, for example, or some other parameter, you are going to change maybe the direction or something like that, or the length of the steps by a little bit. And so there's this so-called bullwhip effect where minor changes amplified over a super long horizon dramatically change the late training or like the behavior late in the run. And like, I mean, we can like visualize it of like, okay, like error like that, error like that, error like that is the updates. If we change like the angle of each one, becomes a bigger change there, bigger change there. And so your final loss, even though you've only made a small change at each step, your final loss is dramatically different. But if you're averaging over all the runs, it's the average of this distance versus this distance versus this distance. So you get this variance reduction effect based on the fact that like, your behavior is not going to change as dramatically. Does that answer your question? Right up there's a chalkboard here. That's convenient. Okay. Any other questions on this before we keep going? Okay. So cool. So I run this. Okay, so now let's run our meta optimizer. So we need to train our meta optimizer, which means we need to specify an optimizer for our optimizer. Here, to not make it too confusing, we're just going to use sort of off-the-shelf SGD as our meta level optimizer. So this is just SGD as you would expect it. It's just, you know, your parameter minus your learning rate times your gradient. Okay, we're going to initialize our meta level optimizer to be SGD with a learning rate of 0.1. Okay, so just to make this super clear, this optimizer, meta opt, is optimizing the parameters of our optimizer. Okay. We're going to initialize our our optimizer parameters. So here we're going to specify our initial learning rate, and this is the learning rate and the decay that we're optimizing. We're going to initialize them to be 0.01 and 0.9. So we know that from our hyperparameter search earlier, we know that these don't work all that well. So these are like relatively poor choices to start off. And we're going to initialize our meta parameters here. So what those meta parameters are, again, is that learning rate and decay. We're again going to grab our value and grad of our meta loss function. So what this means now is what this value and grad of the meta loss function is our meta loss is our whole training loop, and then returning the average of the losses for that training loop, and we are computing the gradient of that average loss. So this is, differentiating a whole training run. As I mentioned earlier, I talked a lot about using like ES, PS, things like that. Here we're computing just analytic gradients. So this is the same gradient that you would get, just via standard backprop. For our meta level training, we're going to train for 500 steps, and the run length of the inner problem is going to be 100. Okay, so as opposed to training over like a full 1,000 steps, something like that, we are only going to compute our meta loss over a horizon of 100. And then the question of whether it generalizes to longer problems is like something we'll have to determine. Okay, so some bookkeeping, and then we're going to just do a simple loop over our number of meta training steps. We're going to get our data sequence. So every single time we're doing a loop in our meta training, we're going to get a different data sequence to run the training on. So this is making sure it's not always seeing the data in the same order. We have to deal with our keys manually in JAX. So you have to be a little bit more thoughtful, but this is just basically randomness bookkeeping. You're going to get your meta loss and your meta level gradient from that differentiated meta loss function. And then we're going to store that. And then we're also going to store the learning rates and the decays over the course of training. Okay, so this is just seeing how they evolve over the course of training. Cool. So let's start off by running this, and I'm going to print every 50 time steps, I'm going to print the meta loss over the course of training. So we'll run this, and we'll see how it goes. Okay, so meta loss at the start of training, 2.3. So it, not training too effectively at the start. Cool. So after 50 steps, the meta loss has dropped to 1.3, meaning that's the average loss over the course of inner training. So it's clearly learning to optimize because that meta loss, we know that because the meta loss is going down. I'll plot the meta loss too, so we can see it. Talk amongst yourselves. Yeah, question. So the learning rate for the meta level problem? Yeah. We're using an off-the-shelf optimizer to train our optimizer, which is like this weird self-referential thing, or like feels like you've just abstracted the problem. But the thing that's nice is that if you are training a general purpose hyperparameter-free optimizer, which is what our goal is, we only need to search over that once, and then you get an optimizer that is self-tuning. So you need to do hyperparameter search at the meta level. Yep. Cool. All right. So this seems to have trained. Let's look at our meta loss curve. Okay. It's going down. Seems good. And let's look at how our learning rates and our decays evolved over the course of training. Cool. So I bet none of you expected the optimal learning rate to be 4.0. It's a non-obvious choice. And the curve is still changing, so I wouldn't necessarily say it's optimal. But a thing to be aware of is that our meta loss is only over 100 steps, right? So it might be learning to be super, super aggressive over that 100 steps to drop loss as quickly as possible by taking these super giant steps that are actually greater than 1. So this is maybe surprising behavior. And then if we look at decays, they seem to be oscillating a bit, flattening out around like 0.6, 0.7. Okay, so let's try this out. Let's, we had a good set of hyperparameters in the beginning. So here I'm calling that our search hyperparameters. So what all of this code is here is doing a training run given some set of hyperparameters. And what I'm comparing is our initial set of hyperparameters that we gave the meta training procedure, our so-called search hyperparameters. So this was like when we did our super course search over learning rates. It was the ones that looked pretty good from there. And then we're comparing that to our trained hyperparameters. And so we can run this and compare them. And we're running this for 1,000 steps. Cool. Okay, so we can see that our initial parameters, our initial optimizer hyperparameters, perform super badly, which is kind of what we expected. The ones we searched over performed pretty well, but the ones we actually trained via meta learning actually do substantially better than the ones we searched over. So this is exciting. I mean, this means that this like actually did something, which is great. So basically, in conclusion, in this notebook, we like trained the hyperparameters of an optimizer using the same basic methodology of what you do in meta learning. There's a lot of things that are very simple in this notebook that look very different in practice. So often we use different gradient estimators, we use different meta losses, we use a distribution over tasks, and most importantly, in this notebook, we're training the hyperparameters of some optimizer, right? So we're learning a learning rate and a decay rate. And in learn optimization, what we want to do is exploit the expressive ability of neural networks to get even better optimizers. So what you could do, and what we, on our GitHub, we have a kind of version of this notebook that replaces the SGD with momentum with a neural network and then trains those parameters to learn an even better optimizer. So, and that's really, that expressivity is at the core of learn optimization. Cool. So that's my notebook. Are there any questions on this before we move on? Yeah. Yeah, that's a great question and like fundamentally at the core of learn optimization, because for SGD with momentum, the answer is definitely yes, right? You can expand your search space however wide you want, and you can grid search in that two-dimensional space. But now let's say I replace your SGDM with the neural network. Do you want to grid search over your 100,000 weights in your neural network, right? Or do you even want to random search that? So it's a fundamental distinction where what we typically do for hyperparameter search is this like randomized grid search. And what we typically do with neural network training is local descent or like local search. And so fundamentally what we are doing in learn optimization is exploiting the interaction between neural networks and local search to learn optimizers as opposed to broadening this global search. Yeah. Yeah, so for a super like low dimensional hyperparameter space, you are much better off using like Bayesian optimization, for example. The problem again is if you go to this higher dimensional space, then something like Bayesian optimization starts to break down, and you also still have to sort of specify your optimizer architecture. So our experience has been that local search on neural networks outperforms any other sort of weight search method. And this is kind of unsurprising, right? Like early in the days of deep learning, people, I assume, I guess I don't know this for sure, tried like Bayesian optimization style methods for the weights of a neural network or like more global search methods. And those were pretty strictly dominated by like gradient descent. For the inner problem or for the optimizer? Okay. So the largest problems that we trained on is probably either a ResNet or a transformer. So like the largest problem that existed in the task distribution that we trained on was probably like a ResNet or a transformer that had a small number of millions of parameters. So like nothing giant, but like reasonably sized. And then in terms of like how far have you pushed the optimizer, maybe I'll hold that question until, so after this I'm going to talk about the state of the art learned optimizer, and that's not the biggest we found, but it's the most effective, and I'll talk about the architecture for that. Yeah. So our state-of-the-art optimizers have recurrent elements that are incorporating history, but they're basically always trained up to some finite horizon. So they always have this like short horizon bias of you're always going to be optimizing performance over some horizon that can't go on to infinity. Cool. Okay, you should maybe move on. Okay. Okay, so good. Yeah. Okay, so that notebook was, doing everything from scratch. We have a software package that's all JAX-based that builds a lot of abstractions that are useful for training learned optimizers. So abstracting notions of tasks or optimizers or meta training pipelines or gradient estimators, things like that all live in this package. And this is the same software package that we use internally to train learned optimizers. We also have like a fairly extensive tutorial sequence of how to use it. So if this is an area you're interested in, I encourage you to check this out. And I want to call out Luke Metz here, who did like most of the software development on this. So I don't want to claim that it's all me or anything. It was mostly Luke. Okay, so with the remaining little bit of time, I'm going to tell you about what our best learned optimizer is right now, and then wrap up and talk about some open questions. Okay, so Velo is our state-of-the-art general purpose learned optimizer, and our goal, very modestly, is one versatile learned optimizer that works for all neural network training, outperforms all current optimizers, and requires zero hyperparameter tuning. So I think most of you can agree that this would be quite appealing. And so we're going to train across a super wide variety of tasks, which are algorithmically generated and augmented, as I discussed. And it's super large-scale training. So this was trained for 4,000 TPU months, which is a lot of compute. This is not the normal amount of compute that they give Google research scientists. My co-authors were very good at finding little pockets of compute that existed at Google at low sort of priority levels, and squeezing some training jobs in there and asynchronously collecting metagradients that would come in. So we basically were using waste compute to train this, as opposed to Google saying, go ahead and take however many millions of dollars of compute or something like that. I also think that we made a lot of decisions in this meta training pipeline that were very inefficient under the knowledge that we were going to do this, training on this async waste compute. I don't think that this amount of compute is necessary to do work in this area, and I don't think anyone, especially students that are here, should think that this amount of compute is necessary. I think there's tons of open questions that you can dig into without a huge amount of compute. And we pay attention to the literature. Anything that you do that is like really impactful will certainly end up in our big runs. And I think you can train very good learned optimizers even with a modest amount of compute. This was mostly just an experiment on how far we could push things given a large amount of compute. So what is the architecture of Velo? On a per weight level, we have a very small MLP that takes as input weight features like the value of that weight, gradient, momentum, normalized gradients, things like that. So this is sort of the features I was talking about. At a per tensor level, we have an LSTM. So this is for each weight matrix that takes as input problem level features. So like how far along in training are you, for example, or what is your loss value? It takes in aggregated tensor statistics. So, you know, the mean and the variance of your gradients, for example. And then what that is outputting is the weights of the MLP that acts on a per parameter level. And the reason we do this sort of hyper network looking thing is because the per weight MLPs are actually too small to be able to meaningfully process an input that's coming from the LSTM. So you get this sort of multiplicative interaction between the LSTM output and the input features that pretty dramatically improves your capacity without having to have a more expensive per weight network. And then at a global level, the hidden states of LSTMs are basically mixed across tensors. So this is a little draw.io graphic of roughly what that looks like. Are there any questions on this? Yeah. Oh, yeah, that's okay, awesome. So what this graph is showing is the process of meta training, but what the different colors correspond to is different set of like meta level hyperparameters that we change during meta training. So concretely, what the main things they correspond to are increasing the inner problem horizon over the course of training. So blue to orange to red is basically changing that, and the orange green overlap is we were training on one horizon, we didn't really like the performance, we rolled back and then kept training with different parameters. That's green, and then red was moving to even longer problems, which is why there's kind of a bit of a jump there, and that helped late training performance. Cool. Okay, so how well does it work? So this is the ML Commons so-called init-to-init baseline, sort of new baseline, and really what it is a set of like fairly large models that evaluation is relatively standardized for. So it's like an ImageNet vision transformer, an ImageNet ResNet, some language transformers, conformer, graph neural network, stuff like that. And so what we can see is that our learned optimizer, here referred to as LOPT, but now known as Velo, pretty substantially outperforms the best tuned atom baseline on most of these problems. And there's a few things to note about these plots. So one is that the two different red colors correspond to training for different horizons, and actually the neural network, the Velo optimizer takes the horizon that you're going to train for as an input. So it behaves differently depending on how long it has to train. And what's really interesting is if we look at this ResNet plot, we see that there's this plateau period, which we basically tried to get around. We thought maybe the optimizer isn't learning to really do anything interesting in that time. Maybe we can just lie to the optimizer and tell it that it's later in training than it actually is. We couldn't ever outperform telling the optimizer the truth about how long it has to train, which I think is very interesting. And what you see on this ResNet plot in particular is that the sort of duration of this plateau phase for different for different run lengths is different. So we don't have like firm 100% evidence that something useful is happening in this plateau, but our experiments have, make us think that there's some sort of useful exploration of some form happening in this plateau. Other things to note, I think that the difference in performance across different run lengths is super interesting. Our performance on graph neural networks is not that good. One thing I would say is that this this graph problem is a little bit unusual just in the structure of losses, but also we didn't have graph networks in our training data set. So our generalization to these graph networks is relatively weak. But for a different graph network that we look at in the paper, we perform a bit better. Yeah.
Early on, I think you graphed Velo with like wall-time, if I remember correctly. Here it looks like 3 iterations. Is it? I imagine it's significantly more. It takes longer to compute, right?
Yeah. So this is a awesome question. For networks of this size, the extra like run length time or like time per step becomes something like 10 to 15%. So the actual extra wall clock time that you have to spend is pretty modest. Yeah. Yeah, I mean, there's some instability in that problem. These tasks are all out of distribution and scale. They're all much larger than what it was trained on, and so there's some instability that it seems to recover from. Okay, a few more results just quickly. We ran Velo on a whole sort of set of vision transformers from the great vision transformer group at Google, who generously ran this for us. And these are sort of across a variety of scales. So all of these are basically out of distribution with respect to scale. What we find is that for smaller vision transformers, we perform as well as or better than the optimizers that they had tuned over the course of several years for their problems. So this is not like an easy baseline. This is their best in-house optimizer. And so we are performing basically at the level or better for smaller vision transformers. And then for larger vision transformers, we start to lag behind. So this is a question of generalization over scale. And then another experiment, they're also super interested in distillation. So they ran an experiment distilling a larger model into a smaller model and actually found that Velo uniformly outperformed the optimizer that they typically were using for that. Okay. We built a set of tasks that are all relatively small, so they run in under an hour on the accelerators that we have. So you can basically parallelize across the set of tasks and get a pretty good metric in a short amount of time. And this is the plot that you saw early in training. So when measured in speed up over learning rate tuned Atom, we find that Velo pretty uniformly outperforms Atom and baselines. And that includes some super strong baselines like Shampoo, which is like a very good quasi-second order optimizer, and a Nesterov accelerated Atom W optimizer that we did a random search over 1,000 different hyperparameter values. So this is a slightly higher dimensional baseline optimizer where we very aggressively tune the hyperparameters and found that Velo mostly outperforms that. A few takeaways, some per task plots. In the bottom left, you have the plots where Velo did the best. So Velo here is shown in red. And what you can see is that one is an MLP where Velo actually is capable of training and most of the optimizers completely plateau, which I think is somewhat interesting. And then another MLP task where Velo just sort of strictly dominates the tuned baseline optimizers. And then you can also see some problems where Velo does less well, and in particular problems where it's beaten by Nesterov or beaten by other baseline optimizers. So the bottom left is the two best tasks within the Velodrome task set, and then the bottom right is the two worst. Okay, so what is Velo doing? We know for sure that it meaningfully exploits larger batch sizes. So we randomize batch size over training, and it seems to have learned to exploit this information. And in particular, the critical batch size. So this is the batch size over which you can't basically trade steps of optimization to batch size, like in a one-to-one fashion. We find the critical batch size is larger, which is important for super large-scale neural network training. As I was mentioning earlier, Velo adapts to training horizon. So this is a training run where we show, a training run for 1,000 steps, 2,000 steps, 3,000 steps, 4,000 steps, stuff like that. So there's meaningfully different behavior for different training horizons. And Velo is adapting to different networks, different layers. The effective step size taken for different parameters in your network does look different. Where does Velo not work? As I've been hinting towards, very large models typically break and don't perform all that well. And I think this is best exemplified in after we got these results, we were obviously very excited. The performance seemed really good. We thought everybody loves language models. Let's try to train some language models. So 1 billion was like quite good. I think 4 billion started to look a little shaky, and 8 billion was like pretty poor overall. And in particular, a very weakly tuned attefactor baseline with a smaller batch size actually outperformed Velo. So generalization to across scale, as I've mentioned, is this very open question that is of huge importance. And I think that this has to be informed by theory of neural network training, theory of learning optimization in general. There's tons of open questions there. And then far out of distribution tasks also don't perform that well. So this is comparing Velo training basically training a PPO task. So this is an RL task, and comparing to Atom optimizers. And what we find is that Atom optimizer can make the ant run in the Joko with PPO, and Velo seems to plateau. So it doesn't work that well on RL tasks. Cool. Before I move on to wrapping up, are there any questions on results? Yeah. Yep. It's the inner learning rate. So what we're telling it is like you are going to train for this many steps. Mm-hmm. Yes. Or like inner optimization problem as opposed to outer optimization. Yeah. Yeah. So there's per tensor magnitude control that kind of looks like learning rate, but also the size of the step that comes out of your per parameter MLP also captures some learning rate. So it's hard to like distinguish in that sense. We we kind of were searching over architecture somewhat randomly without a ton of like theory on how these things should be built. So we added some structure that could be interpreted as something more, some components like learning rate, but I don't think it's necessary. What we're plotting here is like step size. So like what is the magnitude of delta W? Yeah. Yeah, it's inferred. So we don't have an input to Velo that corresponds to some task specification. Cool. I'm gonna keep going and then, or do you have a quick question? Yeah. The hope is that we build an optimizer that can generalize to new architectures as they come out. You know, I would argue that like Atom basically has done this, although there's like a sort of question of whether we've like designed our architectures to be trainable by Atom. But I think like even for new architectures, neural network training problems have enough similarities that we can hopefully generalize to new architectures as they were to come out. But also like attention might actually be all you need. So it's not clear to me whether we actually need new architectures or not. I think that is an important question we should think about. Yeah. Yeah, like self-training learned optimizer. In the Velo paper, we have experiments where we tried to train simpler learned optimizers using Velo, and our experience was mixed, I would say. So, I mean, we know it doesn't work that well on RL, right? And we know that RL and learned optimization training are like relatively similar. So maybe if you had an optimizer that worked a bit better on RL or like ES gradients or something like that, it would train learned optimizers better. But our experience was that Velo does not train learned optimizers that well. Luke and Joshua and a few people, so the group that I'm sort of presenting on behalf of, have a paper where they focus on this question of training learned optimizers with learned optimizers. I'm going to just do my last few slides, and then I'll take questions after. OK, so I really want to emphasize that what I've talked about today has been almost entirely the work of our group, but many other groups have worked on this question and done great work as well. And there's a whole different set of views on learned optimization, all of which is super interesting. So, you know, there's using reinforcement learning for meta training. There's building more sort of structured optimizers that look like controlling the hyperparameters of an optimizer over time. There's learning symbolic optimizers. So there's a group from Google as well that has focused on learning symbolic optimizers. And what I mean by that is specifying an optimizer in terms of a set of functions that are composed as opposed to a neural network. So there's tons of great work in this area, probably by some people in this room, and I encourage you to check that all out. OK, so I'm going to just blitz through this last few slides. There's a few open questions. I mean, there's many open questions, but there's a few I'm going to highlight here that I think are really, really important. And I think that we want to build a black box system that works really effectively. But when you are truly deploying things that have sort of financial impact or impact on people's lives, you are always going to try to diagnose the behavior of that system to monitor it. And so understanding some degree of what these learned optimizers are doing is important in practice. And there's a little bit of work that, again, I'm just going to blitz through, of reverse engineering what learned optimizers are doing. So this paper in particular says, OK, can we see that it is doing gradient clipping? And they dig into it and they say, OK, yes, it seems to be doing gradient clipping. And then it says, OK, can we see if it's using some notion of momentum? And then you build an experiment and you show that it's using momentum. So you can do experiments on these things to extract the behavior, and they require some knowledge of dynamical systems. But you can sort of infer what they're doing, but I think a lot more work is needed in this area. As I mentioned in the first half, I think integrating optimization theory, dynamical systems, and the design of learned optimizers is like a really open question, especially if any of you have backgrounds in dynamical systems. I think there's like tons of work to be doing here. Our work in this area has used very simple theory, so just like quadratic Gaussian problems. There's a whole universe of optimization theory that can be applied to build classes of architectures that achieve some sort of behaviors. I think that simple analysis of forward pass and backward pass moments, so you know, in ResNets, for example, things like this characterization of moments going forward and gradients in the backward pass has been extremely critical in getting supervised learning to work as well as it does. And the exact same thought process can be applied to optimization. And then, as I mentioned earlier, scale generalization is massively important. And I think that we're not going to be able to train at the scale we care about. We have to be able to generalize to it. And so this fundamentally is a question about architectures. Additionally, there's tons of ways to improve meta-training efficiency. I don't think the amount of compute that we used is necessary at all, even currently, but there's tons of contributions that can be made in accelerating meta-training. And I'm gonna skip that figure. Okay, so with that, let me wrap up, say this is what we talked about. Thank you so much. If you are interested in this area at all, feel free to reach out, and I'm happy to talk to you. And there's a link to our code base there. So thank you very much. Yeah. 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 So my understanding is, and I haven't looked at the recent literature, is there is theory on optimal learning rates for certain classes of problems, optimal time varying learning rates and history dependent learning rates for certain classes of primarily quadratics or stochastic quadratics, but they're extremely non-trivial. It's not a clean result by any means. So there's a little bit of theory in this direction. I think that, and then I guess like a lot of optimization theory is focused on best achievable rates and things like that. And so a lot of optimization theory is sort of roughly in this direction. And then once you say, okay, my oracle is giving me much more information than what is typically assumed, or I'm able to use histories in a more expressive way, then I think I'm not sure what the limits of the theory are. Yep. Yeah, so like a neural architecture search style thing. Yeah, we haven't. There are other groups at Google and elsewhere that have worked on neural architecture search. Learned optimization is already pretty complex, and I think that adding in architecture search on top of that would be, there's like clear potential benefits to it, but I think it's also like another ratchet up in complexity that is just a little too much for us right now. Yep. Yeah, it was computing gradients via PPO. So you have your policy and your predict, and using PPO, you're getting gradients out, and then that goes into some optimizer, which typically we would choose Atom. And in our case, we were swapping that for Velo and seeing how well it did.